Hopefully you can hear me. Thanks so much for coming back for part two of this overview of multi-agent reinforcement learning. This is very loud, so I'm gonna move it down. Yeah, so today we're gonna kind of continue on with the overview that we saw yesterday. So again, the same type of thing applies. Please ask as many questions as possible if there's anything unclear, and hopefully you find this interesting. So thanks for coming back today. So we're really coming from this point yesterday that the fundamental difficulty of multi-agent reinforcement learning really came because we had these strategic interactions that were coming because we had multiple agents operating in the same dynamic environment, and those agents all had their different objectives. Their objectives, which might be adversarial to each other, which might just be misaligned, which might be cooperative. Nevertheless, whatever they were, they kind of induced these strategic interactions that really complicated the task of learning. And so what we saw is that they really kind of tend to break our intuition about how we should do learning, about the complexity of learning, but there's still kind of exciting ways forward. And so remember, our main question coming from yesterday was really, how do we design principled algorithms for multi-agent problems? And again, I'm the disclaimer that we're focusing on theoretical foundations. So just to recap where we were yesterday, we're taking Markov games as our kind of formalism for talking about multi-agent reinforcement learning. These are games in which we have a finite action space for each of the n players. A here is just a joint action space of all of the players. There's a joint state space for all of the players. There's a set of dynamics. All of the agents have their own reward function. Those reward functions need not be related to each other at all. And then we were looking at either the finite horizon or the infinite horizon case, and there was an initial state distribution, right? And in a Markov game, if you remember, it was our generalization of a Markov decision process that normal reinforcement learning or single agent reinforcement learning takes place in. Basically, the interaction protocol is like this. At the initial time, the environment will sample an initial action from the initial state distribution. And then for all time afterwards, each agent plays an action A simultaneously into the environment. AT is the joint action played at time t by all of the players. Agents then receive their immediate reward, which is the reward that depends both on the state and the joint action of all of the players. And then the environment will transition to the next state. Right? And this was kind of our very simple protocol for defining a Markov game. And as we said yesterday, we're focusing mainly on the full information case, fully observable and tabular Markov games. So Markov games in which the joint action and states are observed by all agents at every time, and tabular Markov games where there's a finite set of states and a finite set of actions. Great. So if you remember from yesterday, the players are assumed to optimize over their space of policies. And they had three, we kind of considered three different classes of policies. One was a general history-dependent policy. One was a non-stationary Markov policy. These policies can depend both on the current state and the current time. And then a stationary Markov policy, which depends only on the current state. And remember, a policy goes from state to a distribution over actions by which the actions will be sampled at time t. Great. I'm going a little bit faster this initial part just because it's a recap of what we saw yesterday. But then we saw these two different objectives that agents might have in these Markov games. The first is a finite horizon objective, where an agent would like to maximize over their space of policies their cumulative reward over the horizon. And then the infinite horizon objective, where they like to maximize their discounted cumulative reward. And every player can have their own discount factor. And these are the two situations that we saw. And so just to recap, the special cases that we're interested in normally are, obviously this generalizes a single agent reinforcement learning problem. But an interesting case is a fully adversarial or a zero-sum case where we have only two players and one player's reward is the negative of the other player's reward. And then maybe another interesting case is just a cooperative case where everyone is trying to jointly optimize the same reward function, right? And so that's just a complete recap of what we saw yesterday. Because, as you remember, all players are trying to optimize their own objectives, but they're all coupled. The natural solution concept that we've kind of been looking at was a Nash equilibrium, right? And a Nash equilibrium is a joint policy where no player has an incentive to unilaterally deviate, right? So if everyone else is fixed, I have no incentive to change my policy to increase my reward or increase my utility. Great. So we said that this was always guaranteed to exist in Markov policies and Markov games. It exists in stationary Markov policies in finite horizon games and stationary Markov policies for infinite horizon games. So yesterday we kind of started to get some intuition for this problem by looking at normal form games, which are just Markov games with only one state. We saw, that equilibrium computation in general is just very hard, even in really simple games. So the coupling between agents gives rise to non-stationarity and complex dynamics if we want to actually use learning algorithms. And we saw other types of equilibrium concepts like coarse correlated equilibria, for which we could actually have algorithms that converge. Then we moved on to looking at policy gradient algorithms in games yesterday. And we saw that generally there was actually no convergence guarantees or no regret algorithms in general for Markov games, right? So, and in zero-sum games and similar games like competitive games, we saw some more positive results. But hopefully, the takeaway from yesterday, I hope wasn't too negative. But yesterday was just a bunch of negative results saying how hard this problem is. And today I hope to actually start giving you algorithms that actually work in Markov games, right? So yesterday, I think I just kept on saying, oh, this is too hard, this is too hard. Today we're actually gonna move on and give you some actual algorithms that work. So today we're gonna focus on value-based algorithms. And so basically what we saw yesterday is that no regret and policy gradient methods don't generally allow us to develop principled or are not principled algorithms for learning in Markov games, meaning they have no convergence guarantees. And in a sense, the reason for that is because they're a little bit agnostic to the underlying structure of the problem, right? Policy gradient algorithms is nothing more than just gradient descent on an objective. And that's, kind of agnostic to the actual structure that's happening in a Markov game. But reinforcement learning and multi-agent reinforcement learning are fundamentally optimal control problems, right? At the end of the day. And so for an optimal control problem, that should basically tell you that, hint to you that there might be a dynamic programming or a value-based approach to solving multi-agent reinforcement learning. And that's what we're going to kind of look at for the first part of today. So for the first part, we're gonna, spend some time looking at infinite horizon Markov games, and then we'll go back to finite horizon Markov games. So we'll do a little bit of a recap. I think Gaurav covered some of this morning. But we can define the state action value function of a policy in a single agent reinforcement learning problem. Q pi is just the cumulative reward starting from state S and playing action A and then applying policy pi for all time after, right? This is what's known as the Q function given a policy pi. So this is our infinite horizon objective, and we could actually rewrite our infinite horizon objective as basically a function as just an expectation over the discounted state visitation frequency under pi of Q pi, right? And so all I'm doing, this is just an equivalent reformulation of this. I'm just changing notation, right? And hopefully you could see how this follows, almost directly. Great. So we have basically an equivalent formulation of the infinite horizon problem. And Bellman's principle of optimality says that the optimal policy must satisfy this kind of this Bellman equation here. So Q star should basically satisfy this kind of fixed point recursion. So Q star should be the expected value under S and A of R plus the discount factor of the max of A prime of Q star at the next state, right? Where the next state is taken according to the underlying dynamics. This is nothing but the optimality principle for dynamic programming. So basically solving and from Q star, if we have Q star, we could back out the optimal policy, right? The optimal policy is just any distribution over the argmax set of Q star, right? And any distribution over the argmax set of Q star would give us an optimal policy for this reinforcement learning problem. So basically that says that, just finding Q star is actually enough to solve this reinforcement learning problem, right? And this has given rise to this whole kind of separate line of algorithms from policy gradient algorithms known as Q learning. So basically, we can just solve for, we can try and find Q star. If you kind of look at it, Q star is the fixed point of this mapping here, right? So I could define a mapping T that goes from, R of S cross A to R of S cross A. And basically Q star has to be the fixed point of this map here, right? So T of Q star should basically satisfy this. It's just, augments by inspection. And, kind of a very classic result in reinforcement learning is that T is actually a contraction mapping in the L infinity norm, right? So if I just keep on applying T, I'm going to basically converge to Q star because it's a contraction mapping with my discount factor as the contraction, right? So as long as my discount factor is strictly less than 1, this is going to converge, geometrically to Q star. This also tells me something. It tells me that the Q star is unique, right? So that's fantastic because, this very simple observation, right, that we can define this one-to-one mapping, T, and that this mapping is a contraction mapping, basically allows us to immediately develop, and this was what Watkin did in 1989, basically derive a Q-learning algorithm. And this Q-learning algorithm is very simple. This just says for all states and all actions, you're just going to basically, slowly iterate, you slowly update Qt with this contraction, right? And the actual Q-learning algorithm that we all know and love is really just using stochastic approximation of these dynamics, basically building a stochastic estimator of this second term, right? And so that's basically the very kind of famous and classical Q-learning algorithm in single agent reinforcement learning in a kind of one slide. So maybe this was all for single agent reinforcement learning. We could ask, is there an analog to Q-learning in Markov games? Any questions before I go on?
You could also write iterations in terms of value function rather than the Q function.
Exactly, yeah.
Are there strong advantages to doing it in this manner?
Not really, but you'll see why we could do exactly this, the value iteration version of this. It's just Q-learning has better, it'll notationally work out nicer in Markov games. So I'm just focusing on Q-learning.
Not in terms of performance, yeah.
Yeah, not in terms of performance. What we'll actually see, I mean, you're asking a very good question. I'm going to develop most of the work based on Q functions. And then at the end, we'll actually see that value functions are actually more useful objects to operate in. But Q, just for intuition, I think a Q function is a little bit easier to understand. Thanks. But that's you're 50 slides ahead of me. Cool. Any other questions? Cool. So yeah, can we derive a Q-learning algorithm for an infinite horizon zero-sum Markov game? So we're going to focus initially on zero-sum games. And surprisingly, the answer is yes. So this is our classic Q-learning optimality condition. And Littman in 1994 basically built off of the classic result of Shapley. Shapley actually looked at the state value function as you suggested to show existence of a Nash equilibrium, but he didn't come up with an algorithm. In 1994, Littman basically derived min-max Q-learning, right? Basically, the observation was that the optimal Q function in a zero-sum Markov game should satisfy this kind of Bellman principle. That Q of S, given the joint action, should basically be this. But instead of a max, we've replaced the max by a min-max over A1 and A2. And actually, this should be policies. Sorry, there's a typo there. Great. So yeah, he was building off of very classic work by Shapley, who, if you remember, introduced the notion of a Markov game. And Shapley showed the existence of a Nash equilibrium by basically looking at the state value function. And then Littman basically developed minimax Q-learning. So given this, we could actually once again observe that this is a fixed point of some one-to-one mapping. So H now is going from R cross S cross sorry, R to the S cross A1 cross A2 to R to the S cross A1 cross A2. And so, yeah, H is basically just this mapping. And once again, you could observe that Q star is basically just the fixed point of this mapping. That is our questions, I think. Yep.
Quick clarifying question. What's S prime in the first?
Here?
Yeah.
So S prime is the next state given S, A1, and A2. So under the dynamics.
So in the second line, you have a conditional expectation.
Oh, yeah. So basically it's just because S prime is basically fully defined by S, A1, and A2.
So it's the same expectation? Or?
Yeah, sorry, there's a typo here. There should be S, the expectation of S prime given S, A1, and A2. Yeah, thank you. That's a good point. Yep. Yep, these are two-player games. A1 is, the action of let's say the max player. A2 is the action of the minimizing player, right? Because we're in a zero-sum game. Any other questions? Yep. Yep. Yeah, that's a very good question. So there is, oh no, sorry, so I didn't write it. But basically, if you were to take the argmax and the argmin, so basically the Nash equilibrium of each of these stage games, that would basically give you the Nash equilibrium policy of this zero-sum game. Yep, and it need not be unique. Yep. Right? So again, kind of observe that, Q stars is the fixed point of a mapping. The reason why it's okay that it's not unique and we don't have this equilibrium selection problem is because this is a zero-sum game. And so in a zero-sum game, all Nash have to basically give you the same value, right? So the recursion is kind of, gonna be the same value. Any other questions? Great. And so just like in the single agent setting, you could actually show that this new mapping H is also a contraction mapping in the L infinity norm, again with the same contraction factor, the discount factor. Technically, it's the max of the two discount, or actually, sorry, it's a zero-sum game, so it's the same discount factor. So you have a contraction mapping in the L infinity norm, where the discount factor is the kind of contraction factor, right? So the nice thing about zero-sum games is it tends to parallel exactly what we saw in single agent reinforcement learning. That's great because again, we can immediately derive the minimax Q-learning algorithm as basically just iterating on this with some step size alpha. But the only difficulty, right, is that if we look at the definition of H, we have to solve this game at every iteration, right? Instead of just being a simple max that we could do in closed form, we now have to solve for a zero-sum game given the matrix QS prime. Any questions about that? So this is, even though we could write down this algorithm, it's actually still quite complicated to actually implement because we have to constantly solve zero-sum games at every state. Yep. How it came about? Yeah, so basically what you could think about is that it comes from, it's a dynamic programming argument. So if you looked at and we will look at the finite horizon version of this later on, right? And in the finite horizon case, what you do is you start at the final time step, and then you work backwards in time, right? At the final time step, you just have a bunch of matrix games in each state, right? So you solve for the zero-sum game there, and then you recursively will feed that value back in. And then to come up with a new Q function for state at time, t-1, those will define a whole new set of matrix games that you will then have to solve in the zero-sum games on, and then you recurse back all the way to the initial time. And so this is really just that thought process, but for an infinite horizon problem. Yeah.
So Eric, the zero-sum game in two players simplifies analysis considerably in many settings. Can one think of a version in multiplayer game which is zero-sum?
I'll get there. I'll get there right after. Yeah.
So some players when some players lose and they even out?
Oh, so like you mean like an n player zero sum game?
N player zero sum game. Can one think of a version of that?
Yeah. So
With-
there are versions of n player zero sum games. A lot of the times they don't inherit a lot of the nice properties of two player zero sum game unless the zero sum structures are pairwise. If there's kind of more couplings between the players, most of the time all the structure kind of breaks. But pairwise zero sum interactions tends to work. So you'll see there are some papers that look at games where, you have games on a graph, and then all of the interactions are either zero sum or fully cooperative, right? And on those types of problems, those might, those look like general sum problems, but you could actually solve them because the interactions are all, of the type that we could actually, that are nice for analysis.
So I guess the n player zero sum game is essentially same as an n-1 player arbitrary game.
Sorry?
I guess an n player zero sum game is same as an n-1 player general game, right? Because you can just set the last player's reward to be negative of
That's
everybody
true.
else's.
Yeah,
So-
exactly. So it's still quite hard unless things are pairwise. Yeah. Okay, that's a very good point. Great. So yeah, we can basically derive this algorithm, but again, it's not computationally very easy to do because we have to solve these matrix games at every step. Yep. So if we look at solving this min-max problem, this is technically not a very good notation. I feel like I've written it better later on. So what the matrix game is, it'll be a little bit clearer in a sec. Yeah. Thank you. Sorry about that. Yep. 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 Yeah. So the nice thing about a finite horizon game, we'll get there later on in the talk. But even in single agent problems, right? The existence of a solution doesn't rely on contraction. It's really just, backwards recursion. Okay? And that's exactly what's going to happen here. And that's actually why basically, finite horizon games have such nicer properties than infinite horizon games because we don't need a contraction to, prove that algorithms converge. But that's a very good point. We'll come back to that. Yep. Yeah, sorry, that's the typo actually. So A1 and A2 here are actions, but they should be mixed strategies. Yeah. Yeah, I mean it is an LP, so you could implement that and it's fine, but it's still more complicated than solving just a max, right, over a finite dimensional vector. But yeah, that's all I meant. It still requires you to solve a matrix game, which in very large spaces is maybe hard. Yeah. Great. So the unifying idea to actually make this like maybe an implementable algorithm is again this idea of timescale separation, where the idea is we're going to solve per state matrix games on a very fast timescale using something like no regret learning. So any of the algorithms that we saw worked for normal form games yesterday. And then on a slow timescale, we're actually going to use minimax 2 learning. So let's look at how that works. So this is, I'm calling it just the centralized computation of Nash in a zero-sum Markov game. We're going to initialize Q0 and the policies for all of the players, arbitrarily. And then for each step, for each state, we're going to update the policy using a no regret learning algorithm on this matrix game. This is the kind of right definition of a matrix game that I was looking at. So basically, we're going to solve for a max, min, given S, given a fixed state of this object here. Where Q, if you remember, is now just a matrix in A1 cross A2. Right? So this is really just a matrix game given the state. Right? So for example, we could just do policy or gradient ascent descent on this objective. Right? This is the gradient with respect to pi1. This is the gradient with respect to pi2, but negative because they're descending. Right? So this is a very kind of simple algorithm for solving these matrix games. And then on a very slow timescale, we're just going to update our Q function like this. We're going to do Qt plus 1 is equal to some step size Qt plus beta times the reward at the state and the value that we've currently computed, right, for this game. So we're going to assume that alpha is much, much greater than beta so that these converge to the value at a fast rate. And then on a slow time scale, this is actually exactly implementing minimax Q learning. Oh, and sorry, there's another typo. There should be S, there should be an expectation over S prime. Sorry about that. So the principle is very simple. The idea is just we're going to solve these matrix games. We're going to solve each of the matrix games in this expectation on a very fast time scale. And then on a slow time scale, we're just going to implement this algorithm. And the idea is if we're solving the matrix games faster than this iteration is updating the queues, then we're basically going to perform this algorithm on the slow time scale. Great. So this is actually a pretty general algorithmic principle. There's a lot of papers that actually use this structure. So there's a lot of papers that use no regret learning subroutines and analyze basically full information algorithms. Several papers have actually started to look at sample-based algorithms for solving these. But I should just mention that this is really still an ongoing area of research. If you look at these papers, these are all from the last couple of years or so. But before kind of spending too much more time on that, I'd like to think about whether or not these ideas extend beyond the infinite horizon case.
So are there clear ideas on the relationship between the step sizes alpha and beta?
Yeah, so some like these papers all have kind of different conditions on the step sizes depending on the subroutines that they use. So in the full information case, you have basically a very clear idea of what they are. I think this paper has just like a finite timescale separation that you need to satisfy. This paper, I'm one of the co-authors on this. So this paper uses basically decaying step sizes. And it's basically just the normal kind of timescale separation argument. So you need one sequence of step sizes to go to 0 and then the ratio to go to infinity.
But in those papers, they actually can give structural insights depending on.
Yeah. It really just depends on the subroutine of a no regret algorithm that you use in this step. Some no regret algorithms converge much quicker, especially using constant step sizes. So for example, proximal point or extra gradient algorithms, they'll converge in a last iterate sense with using only a fixed step size. And if that's true, then you could actually understand better the step size that you would need on the slow time scale. So it just really depends on the two pieces that you're putting together. But this is just kind of like the general algorithmic principle that people use.
It's a hard problem, right?
Yeah, it's a very hard problem, especially when you're looking at it from a sample-based viewpoint, because you're updating S, you're getting samples of the reward, and so you have this problem of you're trying to explore this MDP. You have kind of actually non-Markovian noise, and it's very ugly. There's a lot of moving parts. Yeah. So the analysis in these papers is not easy. This is a very very general simplification of what those papers are doing. But just the algorithmic principle is quite simple, which is why I wanted to keep it at that level. Great. So yeah, a lot of kind of algorithms kind of use that principle. I'd say actually almost all the algorithms that we know that have strong convergence guarantees and zero-sum Markov games rely on this principle here of very quickly solving the matrix games, very slowly updating the Q function. You could think of this as an actor-critic algorithm if you're familiar with that from a more reinforced learning setting. You could think of these as basically being the actors and then this being the critic, or a very slowly varying critic. It's okay if those are all words that you don't know. Great. But I'd like to go on beyond zero-sum and see what we could do. And see if any of these ideas actually extend beyond zero-sum games. So there's actually a paper that came out, maybe 10 years later that was called Nash Q learning, right? And the idea here was, hey, we had a lot of success replacing our max by a min-max. What if you just replace the min-max with a Nash, right? The Nash value for agent I, given the Q functions for each player, right? So again, in Nash Q learning now, it's a little bit uglier. Every agent has to keep track of their own Q function because the Q function, depends on their own reward, right? And then, this Nash is just replaced with that value at Nash given the state-dependent matrix game, right? Which is just the expectation over A from the joint policy pi star, where pi star is the Nash equilibrium of given Q1 all the way to Qn at S prime. Great. Yep. So this is just like your payoff at Nash, right? This quantity here is really, yeah, how do we compute it? That's a very good question. We actually don't know how to compute that in general, right? That's actually exactly what makes Nash Q learning not tractable. So I should say this immediately reduces to minimax Q learning in zero-sum games. But there's also other problems. There's equilibrium selection problems, right? In more general sum games now, right? The Nash might not be unique and the Nash value might not be unique, right? So you have to be very careful about which ones you use. And so unfortunately, you actually can't show that this is a contraction mapping in general. This is true even if you replace Nash with maybe a correlated equilibrium or a CCE, right? And basically the only known cases where you get a contraction mapping is in zero-sum games or fully cooperative games, right? So even though that you could define this algorithm, it's not actually implementable in a much larger class of games. Great. And so that kind of, ends our analysis of infinite horizon Markov games. So in general, we have no algorithms actually for solving infinite horizon Markov games beyond highly structured games like zero sum or cooperative, right? And that's kind of the takeaway I'd like you to have, is that, we actually don't have algorithms that can compute stationary equilibria in general sum Markov games. It's actually, to the best of my knowledge, just not possible. That in some sense shouldn't surprise you given all of the hardness results we saw yesterday. But it's interesting in a sense. So in infinite horizon zero sum Markov games, we actually can develop algorithms. And so the main idea that we saw was really this idea of a timescale separation. And yeah, again, this hardness shouldn't be, very surprising given what we saw yesterday. So, luckily in finite horizon games, there's a lot more to say. And so that's where we're going to go now. I should mention, one way of getting, solutions to infinite horizon games is actually just to treat them as finite horizon games. So you kind of pretend like there's some kind of finite horizon for the problem, and you solve for these finite horizon equilibria that we're about to talk about. But that's a different.
Sorry, can you map these infinite horizon problems to some hard class of problems?
Yeah. So computing a Nash in a general Markov game is also in PPAD, right? Just that's like a complete, just because the one state version is in PPAD, this has to be. But there was that paper that we discussed yesterday by Daskalakis et al. And there's another paper that kind of came out at the same time that showed that even correlated equilibria or coarse correlated equilibria are PPAD hard in infinite horizon games. So in a sense, those are just too complex a class of games. And we need to understand, are there versions of infinite horizon games that have more structure that we could actually give better convergence guarantees or better algorithms for? But that's, as far as I know, a pretty open question right now. Great. Any other questions about infinite horizon games? Mm-hmm. 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 Yeah. So the reason why you need a kind of a contraction is because you want these, it's easy to see. Sorry, give me 1 second. Yeah, if you look at this, the reason why you want it to be geometrically decaying is because you want this to be finite, right? Because it's an infinite sum, right? So if it's not geometrically decaying, this is infinite always, right? And so that's why it's always geometric. Yeah, otherwise the problem is not really well posed because otherwise your utility is always infinite. Yeah, I mean that's basically almost something similar to this. Yeah. Oh, faster than geometric. Mhm. Mhm. Yeah. So I think if you have a discount factor that decays too quickly, that's probably essentially making it just a finite horizon game, right? And so what we'll see is as soon as you have a finite horizon game, the picture gets a lot nicer. So you're about to see basically that case would work for this because you're like we haven't really defined it, but you could do just time varying rewards, and so what you're suggesting is just a time varying. But yeah, I mean that's good thinking, right? Like, how do we start overcoming these difficulties of these formulations? Cool. Any
So,
other questions? Yep.
Yesterday we saw that finding the optimal policy in Markov learning, Markov games was p-pad hard.
Yeah.
Is that why this is hard? Because if
Yeah.
you're good at if you can solve Q learning fast,
Yeah.
that automatically implies
Exactly, yeah.
an optimal policy, and that is hard. So this is hard.
Yeah, exactly.
I
Right?
see.
So there's no free lunch, right?
Right.
That it's just that hardness is exactly what's driving this, right? What's your intuition is right. If we could actually solve this, then we would have a solution, and we can't have a solution. So yeah. But it's just useful to see from this other point of view. Great. Any other questions? Great. So now I'll move on to the finite horizon setting. And the nice thing is we're going to go back again to just the single agent setting. And in single agent, the nice thing about the finite horizon setting is that we can basically always find the optimal policy. Now, not via any contraction mapping argument, but just via dynamic programming, right? So we could basically just initialize, QH+1 to be 0, and then go backwards in time. And then for each state, we're just going to, recursively update, given QT+1, the max of QT+1 under this expectation, right? And again, this computes the optimal time-dependent now Q function, which we can use to infer the optimal time-dependent policy in normal reinforcement learning, right? And this is again just dynamic programming if you've ever seen it, right? So you're proceeding backwards. The important thing is that there's no contraction mapping argument here needed, right? We're just working backwards in time, and we're just kind of constantly solving this max, and all of the objects are well defined, and so we could just recurse. And so that gives rise to a very kind of simple algorithm known as Nash value iteration, right? Which is that we initialize for all agents our Q function at ht+1 equal to 0. And now the value at time ht+1 equal to 0. And then again, working backwards in time, we're just going to update our Q function in this very simple way. The expected value under S prime of your value at time t+1 plus the reward. And now there's no discount factor because we're in finite horizon, right? And we're just going to update the Q function at time t with this value here. And then for each agent I and for all states, we're going to solve for the Nash given Q1 to Qn, right? We're going to come up with the Nash policies. And then we're just going to update our value at time t as basically the Nash value for player I, given this Nash equilibrium. And so we can solve a matrix game at each state and time for every time in the horizon. And we'll just keep track of the state value function. This is where, again, the state value function becomes useful to think about. So again, this is just nothing more than dynamic programming. We're starting at time h. At time h, Q, VHT+1 is 0, so this quantity is 0. So we just solve a bunch of matrix games. And then we're just iterating backwards. At each time t-1, we solve a bunch more matrix games. At time t-2, we solve another set of matrix game, and so on, all the way to time t is equal to 0. Yep, any questions about this? No, yeah. I mean, you could define it in like an optimization sense, but it's not optimal, right? Because you're like, given that your opponents are fixed, you could always deviate to a non-stationary policy that would increase your reward. Yeah. Cool. Any questions about this dynamic programming formulation of Nash? Great. Again, right, we still have to solve this matrix game, right? And so there's still this fundamental hardness because we know that this is hard in general n-person games, right? But I should say, if you could actually solve for this, it computes a Nash of a finite horizon Markov game, almost by definition. And it does this in polynomial and the horizon, the state space, the size of the action spaces of both players, given this oracle of a Nash. I should mention that computing this Nash is what's hard about this algorithm. I would also kind of like to point out that equilibrium selection isn't a problem here, right? Because you could use any Nash, any of the Nash, and just propagate it backwards in time, and you would get just a different Nash equilibrium for the entire game.
What if you approximate the Nash?
What do you mean? Sorry.
Instead of solving it exactly, the Nash problem.
Oh yeah. You'll probably just recurse a bunch of. Yeah, that's a good question. The Nash.
Are there inapproximability results for this or something beyond a point?
That's a good question. I mean, there's just the hardness of computing a Nash of this is really the hard part. If I go to the next slide, we're gonna actually just replace this by a coarse correlate equilibrium, and then approximating CCE, that is gonna be fine all the way. So if you approximate a CCE at each step, and then you still do this dynamic programming, the result is gonna be approximate CCE. That might not be true about Nash, because Nash are very sensitive to perturbation.
So you mean the Nash being computed approximately is also hard? Beyond
Yeah.
a point, I see.
Yeah.
I see.
Yeah. Great. So yeah, computing a Nash equilibrium is hard. And so, something that people often do is actually switch to computing a coarse correlate equilibrium, or a non-stationary Markov coarse correlate equilibrium. And again, you could do this via dynamic programming, where all you're doing is replacing the Nash with a CCE here. And you could solve this using, again, linear programming or just no regret learning in general, right? So the nice thing now is that we can now compute a CCE of a finite horizon Markov game in polynomial number of steps in all of the relevant problem parameters. Any questions? Great. So now we'll move on, and we finally will get to actually learning. So far, we've assumed that you basically know the Markov game perfectly, right? And we've only really looked at the problem of computing an equilibrium, right? We haven't looked at anything to do with learning beyond, no regret learning. But the real struggle in reinforcement learning is you need to learn, right? And you need to learn both the dynamics of the environment and the reward function to some extent. So you need to basically trade off your exploration of the environment with your exploitation to actually accumulate reward. And this is really the crux of the normal reinforcement learning problem. In multi-agent reinforcement learning, you not only need to learn, but you need to learn the dynamics, the reward, and you also basically need to learn how to compete effectively, right? And so this is a much more general and more difficult problem than single agent reinforcement learning. And we could think a little bit about how you might want to explore an environment, right? So in reinforcement learning, there's been a lot of recent progress on how you might optimally explore a Markov decision process, right? So we've seen, maybe the most famous one is epsilon greedy. At each step, you either, randomly choose an action with probability epsilon, or you, operate according to your current policy, right? And that's, epsilon greedy exploration, which is, something pretty naive. And this can be shown that in the worst case, this can take an exponential number of samples to actually learn a policy. It doesn't use the structure of the problem very well. But in reinforcement learning, there's been a huge amount of work on how you might actually explore a Markov decision process optimally. And one of the algorithms for doing this is basically based on this idea of optimism, which is that you basically construct an upper confidence bound of your Q function in every state and for every action in that state. And then you pick the action with the highest upper confidence bound. And what you can actually show is that this strategy yields a statistically optimal way of exploring an MDP for multi-arm bandits and for reinforcement learning problems. So that gives, if we kind of use that exact same principle, we can come up with an actual learning algorithm based on that dynamic programming formulation for Markov games. And that's what's known as optimistic CCE value iteration. So the algorithm is quite simple. You initialize all the agents. You initialize all the Q functions for all the agents to 0 at time ht plus 1, and all the value functions for all the agents at ht plus 1 to 0. And you initialize all the policies, again, arbitrarily. Then at each step, you execute the current policy, you collect rollouts, and you estimate the transition policy p hat based on the number of times you visited each state. You've basically seen every state action and transition pair in your set of rollouts, given the current policy. And then you kind of essentially just do dynamic programming. So for t is equal to h all the way to 0, you're basically going to update your upper confidence bound on the Q function using exactly the same idea, but you introduce an upper confidence bound term here, which depends on the number of times you visited each of the states. And then you basically compute the CCE based on these upper confidence bounds. And then you update your value, right? And the idea here is that you're constructing an optimistic estimate of your Q function. This is a high probability overestimate. So you're actually, so this is what's giving you exploration of your environment. And you could basically choose this UCB term, doing some concentration inequality type of analysis. And you're again using this kind of CCE oracle, right? And this algorithm can be seen as a multi-agent extension of a very kind of famous algorithm for single-agent reinforcement learning, known as UCB value iteration. But there's some really nice work in kind of 2020 that showed that with high probability, this optimistic value iteration algorithm finds an epsilon approximate Nash equilibrium in zero-sum games in basically a number of episodes that scales with h cubed s, the number of actions for agent 1, the number of actions for agent 2 over epsilon squared, right? So it requires basically a polynomial time and polynomial number of samples are required to compute this epsilon approximate Nash equilibrium of a zero-sum game. They also show in this paper that there's basically a lower bound. There's a fundamental hardness proof for this class of problems that any algorithm needs at least this many episodes and this many samples to actually compute a Nash equilibrium, right? And so you can see there's a slight difference here in basically the dependence on the number of actions. And so yeah, any questions on that before I keep going? So we have come up with an algorithm that actually explores the Markov game. We can now look at what the convergence proof looks like for a CCE. The convergence rate is a little bit worse. We now pay h to the 4th and the product of all of the action spaces of all of the agents. I should mention that this is now computing an epsilon approximate CCE of the Markov game, but this algorithm that we just defined is actually not a no-regret algorithm. So that's maybe a little bit surprising. This is an algorithm that isn't no regret, but that is outputting a non-stationary CCE for this game. So that kind of jives with the work that we saw yesterday. And again, there's a lower bound here, which is that basically we should actually only pay for the max over A, not the product. And this last part is if we look at the lower bound versus the number of episodes, we could see that the lower bound only suggests that we should pay for the largest action space amongst all the players. The upper bound basically says that we're currently paying for the product of all the action spaces, which is basically something like a to the n. And so this exponential dependence on the number of players was called what's known as the curse of multi-agency. So this is an analog to the curse of dimensionality, right? And so a lot of algorithms that you might use for actually learning in multi-agent games, if they're not well constructed, suffer from this curse of multi-agency, this this kind of exponential dependence on the number of players in the game. And so overcoming that is basically an active area of research, and we'll go into that a little bit more in a sec. But any questions on all of that? I know that I went through that a little bit quickly.
Are these kind of matching in the single player setting, the upper and lower bound?
Yeah. Yeah, in the single agent setting, we have, like, I think this UCB VI algorithm actually achieves the lower bound. But in the multi-agent setting, it doesn't anymore. And it's exactly because of this curse of multi-agent.
So this h cube and h to the power 4 difference is not there in the single level. So
No, yeah. We have, I mean, there's been a huge amount of work, and I think probably Gaurav will talk about it. But yeah, we basically have optimal algorithms for single agent RL. Yeah. Especially in these tabular cases. Great. And so, yeah, the problem is if we, what I really liked about this paper is that it exposed this curse of multi-agency, which, haven't really been, explicitly brought out before. And, this could be a potential problem if we want to actually scale these games, right? If we want to really look at large games with large number of players, an algorithm that pays something exponential in the number of players just becomes unfeasible to actually deploy, right? And so, there was a lot of work afterwards on is this a fundamental hardness, or can we actually come up with algorithms that achieve this lower bound? Great. And so if we look at it, if we look at maybe why this problem is occurring, we could see that the size of the Q function itself in games, already makes us pay this factor, right? The Q function itself, is basically living in R to the S cross the product of all of the A's, right? Because the Q function depends on the current state and the joint action of all of the players. And the joint action of all of the players lives in this product space. So if we try and, design any algorithm based on Q learning for games, we're almost necessarily going to have to pay this cost here. Right? And so that kind of came to this new idea that, if we look at Nash value iteration, we actually only ever need to calculate the value at a CC and a Nash. We don't actually ever need to compute the Q value, right? And that goes back to your earlier point. And so the idea is could we come up with an algorithm that only operates based on values, right? In games. And the idea now is really to use essentially timescale separation as our key tool, right? There's only one trick in this literature. And the idea is on a fast timescale, you're computing an optimistic value based on no regret learning. And on a slow timescale, you're updating your values using dynamic programming. And we'll see what that looks like on the next slide. But the crux of the idea is really just that the sample the reason why we might hope that this works is that if we deploy no regret learning, the sample complexity of no regret learning scales as this max over A. It doesn't scale as the product of that dimension of all of the players, right? And that's kind of a very important fact about Q learning. You could even think of projected gradient descent in some sense. It's actually dimension independent, right? Yeah. The convergence. Great. So the idea that they came up with afterwards was to basically use a payoff-based or a bandit feedback, no regret learning algorithm. So these are algorithms like the EXP3 algorithm or stochastic mirror descent. These are algorithms that again kind of guarantee this no regret like behavior, right? So it says that for any arbitrary sequence of losses, LT, we can construct a policy that competes against the best policy. That competes against the best policy, while only playing actions sampled according to the policy at each round and only observing the reward given your action, right? So RTA is actually just the entry of this loss, according to A, right? And it's a very powerful property. So we can see what the algorithm looks like now. So this is this was an algorithm known as V-learning. And the nice thing is it decouples very kind of cleanly across agents. So we only have to look at the point of view of one agent. So this is V-learning from the point of view of agent I. The way this works is that agent I will initialize their policy. Then for each episode, they're going to receive an initial state as 0. And then for all t, 0 to h, we're now proceeding forwards in time. We're going to sample an action according to our current policy at the current time. We're going to observe our current reward, and we're going to observe the next state. we're going to keep track of the number of times each state has been visited, right? And then we're going to compute our optimistic value function using, basically just the same recursion as we saw before. Again, using an optimistic estimate of V. So we're going to have this bonus term to induce exploration of the MDT. This is going to happen on a slow time scale. Alpha is going to be much smaller. And then on a fast time scale, we're just going to take one step of a no regret alpha, right? Based on the action that we got, and then this loss here. And beta is just going to be the step size. It's going to be, larger than alpha. And so, yeah, we're basically going to use an adversarial bandit algorithm on the fast time scale. And, just to see why this works, we could look at, suppose that the fast time scale has converged. Then we could just analyze this last step, and we could see that it's essentially basically just doing this, this stochastic approximation of the original dynamic programming algorithm, right? So basically the reason why this algorithm works is that it's essentially doing stochastic approximations of the dynamic programming algorithm that we saw before when the fast time scale has converged. So analyzing the convergence is, again, a very non-trivial endeavor. But what we can see is that this algorithm is actually going to work. And note that this algorithm here is actually, this algorithm here is actually never computing any Q values, right? Everything is just operating based on the state value function. And because of that, hopefully we shouldn't pay for the curse of multi-agency. Great. And again, note that this algorithm is independent. Players can do all of this separately. They just have to sync these step sizes, right? And so there was a really nice result by Jin et al. In 2021 that basically showed that this algorithm, value iteration, would follow the regularized leader as that no regret subroutine, finds an epsilon approximate CCE in basically this number of episodes, or we've lost a little bit in the horizon dependence, but we get the correct, we overcome this curse of multi-agency, right? There's nothing here that depends exponentially on the number of players in the game, right? And so a similar result kind of came out at the same time by Mao and Basar, using mirror descent instead of follow the regularized leader. So good ideas tend to be discovered at the same time. And then more recently, this was extended to correlated equilibrium by using a no swap regret algorithm as the subroutine. I should mention this is still an ongoing area of research. A lot of people, there are papers that are trying to shave down this to make it match the lower bound as much as possible. A lot of people are working on faster convergence rates more generally, specific structures in which you could actually say something stronger, like extensive form games, cooperative games, zero-sum games. People are looking at how you might do equilibrium selection in these problems. People look at multi-objective optimization through this lens. It goes on and on. But the crux is we finally have developed an algorithm for markup games that has convergence guarantees efficiently to a game theoretically meaningful equilibrium, right? And that was kind of the goal for this talk. So it is possible, even though it's hard. Is kind of the moral of the story. Great. So I think I'm almost out of time for this this section, but I'll just wrap it up. The takeaway is that in infinite horizon zero-sum game, or in infinite horizon case, we could develop Q-learning algorithms for zero-sum games, but not in general, right? The picture gets a lot nicer in finite horizon markup games. We could efficiently learn Nash or CCE, but you have to be careful about the curse of multi-agency. Sorry, this should say CCE. But the takeaway, at least to me, is that the real tool and the real kind of unifying idea behind most of the algorithms in this field has really been to use timescale separation to simplify the problem and deal with the non-stationarity of these problems. And so you should really think of this as maybe the key tool and idea in this field, algorithmically, right? Because it basically allows us to stabilize learning and prove convergence in a very structured way. Great. And so that kind of wraps up what we were going to talk about on algorithmic structures in multi-agent RL. In the next hour or so, I'll kind of talk about some more recent results from my group on function approximation, scalable algorithms with function approximation, zero-sum games, and some kind of future thoughts. But yeah, happy to take questions as we go into the break. Thanks.
By the way, I think
Oh, I thought it was 11:15 or 12:15. Oh, okay. So sorry, I had it as 12:15 on my thing. Okay, so I can go into the function approximation, or happy to take questions. Yep.
Yesterday you mentioned a result that CCEs are not great because there exists some dominated strategies.
Yeah,
able
some
for
CCE, yeah.
segments. So why is this still
A desirable solution.
desirable solution concept?
It's the best that we can do, basically. Yeah, I think that's kind of the answer. We don't have any other equilibrium concepts that we could compute efficiently in these games in general. And so CCE tends to be the best that we can hope for. Sometimes you could strengthen it to a correlated equilibrium, but actually correlated equilibria, I think, still have that property that you could construct a case where it puts support on a dominated strategy. So yeah, it's still.
And these are not pathological examples. These are like very straightforward examples where this happens. Or?
Yeah, there's a paper with a few kind of these examples. They're a little bit pathological, but it's not entirely clear how often they are. I think that to me the bigger problem with CCE is they need coordination to actually implement. So if you take the policy that you learned, take the average policy that you learn, you can't actually go and deploy it in a new game. Because it's not entirely clear that your opponent would ever actually do anything. Well, a Nash has some nice properties from that point of view. It doesn't take coordination to implement, right? So yeah, and CCE also you don't know the quality of the CCE that you're converging to. CCE is a large convex set of solutions. You don't know which one you're converging to. Some might be Pareto dominated by others. So you have equilibrium selection problems. So yeah, in some sense, we shouldn't be like entirely satisfied with this, but it's the best that we have so far. It's a really good question.
Then you could potentially in the faster time scale incorporate some kind of equilibrium selection. Also.
Yeah, you could. You could come up with certain things to maybe bias your algorithm towards higher maybe social costs or higher welfare solutions. But those are mostly ad hoc. I haven't seen anything pretty rigorous about it. Yeah, but I mean, yeah, all of these are really good questions. CCE, I would say, is also very unsatisfying to me, which is why later on we're really going to talk about that. Yeah. Yeah. Yeah, that's exactly what they do in this paper. It's basically exactly this algorithm, but instead of running no regret, they do no swap regret here. Yeah. Yep. And go ahead. Here you're actually converging in your like iterate sense. Yeah. Yeah. Yeah, exactly. Because the reason why that's true is because this is a convex game. Or it's a concave game, right? This is linear. So averages kind of work out. Yep. Yeah. Yeah, so this is, people call it an independent learning algorithm because, I don't need to know anything about your utility, but to actually implement it, we need to coordinate in some sense. I mean, maybe you have to sync across all players who are like strategically linked, right? If your payoff doesn't actually materially depend on anyone else's, you probably don't have to sync with them. But yeah, generally you have to sync across all players. Yeah, yeah, no. I mean, there's there's some works that kind of say like, if I'm learning much faster than you, then I can maybe, instead of doing a no regret algorithm, I can change my gradient estimator and converge to a stackable equilibrium and do better. But yeah, there's not a lot of papers on that, but yeah, there's people have looked into some of these things, but not in any, amount of depth, I would say. Or like, there's not a huge amount of work on it. But it's a good question. Cool. Any other questions before we move on? Yep. Yeah, so in this case, you basically have like a convergence guarantee of the algorithm is going to output a policy that's a CCE, like a joint policy for all the players that's a CCE. Yeah. Yeah, that's a really good question. So basically, what you'll be able to show, you basically output, this algorithm is technically missing a step, which is that you output the average policy of all of your, like your average policy. If you look at the average policy of all of the players, that's going to be a CCE basically, or like the distribute. If you uniformly sample from the policies played by all the players, it'll be a CCE. So that is the case in the rock paper scissors case, where like on average, yeah, when you average, it's a Nash, but or it's always cycling around. Yeah, like the average. If you look at the average history of play, it'll converge to a CC. I think there must be work on like MDPs with delayed rewards. I'm not sure about Markov games. There might be a few. I just am not aware of it. But like all of these twists are very important, and yeah, exactly. Yeah, that's certainly a possibility, and it would complicate the picture a lot. But it would be a very interesting problem because it's very realistic, right? Any delays or anything like this are very real. Any other questions? Yeah, that's a very good question. Again, here we've assumed that every player has the same horizon, right? So yeah, that's a really good question. It's not entirely clear what it looks like. Yeah, you could maybe model that with like discount factors and things, but again, like I haven't seen much on it. It's again, this is a field in which if you look at most of these results, they're kind of very recent. They're all from the last couple of years or so. And so yeah. That's a very good question. I think, most of the time people just tend to use these policy grading algorithms just because they work so well for single agent learning that they just tend to like, blindly throw them into these like large scale, like training multi-agent LLMs or something. But as we've seen, policy grading algorithms don't really have like great guarantees in games. So it's hard to say anything about them. So, I think hopefully people would start to use more value-based algorithms. Just as an example, when I think we looked at a lot at Atari games earlier, right? That Gaurav was going to code up Pong, right? Pong was basically deep Q networks, and again they were trained in self-play, I think, right? So it was technically a value-based algorithm using Q learning with function approximation, playing against itself over and over again. I think AlphaGo was also something a little bit similar, where it was learning a value function to inform the policy. So you could think of them all as value-based algorithms. They weren't exactly using these structures or anything like this, but the theory is kind of lagging a little bit behind the practice, and like most of machine learning these days. So, these multi-agent problems that I think people are very interested in, they range all the way from multi-agent robotics, right? So, human-robot interaction, having robots kind of coordinate self-driving cars. How do you have them navigate intersections, which are like, just fundamentally multi-agent interactions, all the way to like, more cooperative settings. Those look like maybe decentralized control of like energy systems, right? I have each node is locally optimizing its reward, but it's linked to other nodes, through the network. That becomes a game. It becomes a kind of cooperative game, but a lot of these ideas apply. So, anywhere from I'd say like network games to robotics and control, a lot of these ideas I think would be very useful. We'll see. So these guarantees that we can get in this, so, I would point out all these are in these kind of tabular regimes, right? Policy gradient methods so far don't have these like matching upper and lower, like it doesn't match the lower bounds yet, at least from what I understand. Yeah, and we haven't discussed any of that, right? So I think like function approximation is going to be really important. I'll talk a little bit about it in the later part. Actually, that's maybe a good segue. So maybe in the last like 5 minutes or so, I'll just really quickly do this function approximation section because it's actually relatively self-contained. So I'll quickly talk about, this is now work from my group about how we might think, how do we think about using function approximation and Markov games, right? So we've seen a lot of algorithms for efficiently learning, particularly in tabular finite horizon Markov games, meaning that it achieves, really good sample complexities. But, importantly, we've been really looking at tabular cases, so finite state and finite actions. And, these algorithms normally, are, if the state space or the action space is very large, the scaling is not going to be great. And so we'd like to actually use some form of function approximation, right? And we've basically seen, maybe our three desiderata from before. We wanted convergent algorithms, independent learning algorithms, and no regret algorithms. But what we'd actually like most of the time is for them to be very scalable, because even if we, our algorithms and our sample complexity scales linearly in the number of states, that would never have allowed us to solve AlphaGo, right? AlphaGo, the sample complexity, if that's true, the number of states that are possible scale is like 3 to the, it's more than, number of atoms in the universe, right? And so we really have to think about how we can use function approximation in Markov games. And the place where, so basically, yeah, to deal with the scalability issues, to deal with large but still finite state spaces, we have to really use function approximation. To deal with continuous action, continuous state spaces, we also have to do this. So, in deep reinforcement learning, we've kind of seen this pattern over and over again that, the more data, the more compute, and the more kind of complex models that we use, the more we could kind of increase performance. And we could kind of ask if this is still true in multi-agent reinforcement learning. And that's kind of what we did with my student at Caltech, Tinashe. We kind of looked at how we might use function approximation in strategic environments. And I'll take you through kind of like a very kind of simple, mental, intuitive picture of this. Suppose you have n different policy spaces, right? So each of these are different function approximation spaces, or different function approximators you could think of decreasing expressivity, right? So this is maybe think of this as maybe the smallest neural network all the way to the largest neural, right? And suppose this, this is the pipeline of how people might actually go about, using function approximation in Markov games. The learner is going to choose a specific model class, right? And now in a Markov game, they're going to actually train a model and deploy that model into the environment. That learner and the environment are going to settle maybe into a Nash equilibrium. And the question is, which of these model classes is better at Nash, right? Which class of function approximations, or which classes of models or policies should we use in a Markov game, right? Even if we have infinite compute and infinite data, is it clear that we should always choose the most expressive model, right? In reinforcement learning, that answer is true, right? Reinforcement learning is an optimization problem. If I optimize over, over a larger space with infinite data, perfect computation, I should always choose the most expressive model possible, right? And so basically the main question I'm going to ask is, should the learner always choose the most expressive model class if they want the best equilibrium outcome? Best equilibrium outcome meaning the equilibrium outcome giving them the highest utility at equilibrium, right? And we're just taking the point of view of a single agent, right? So, we can already start answering this question. As I said, if the environment is static or we're in a single agent optimization problem, the answer is definitely yes, right? You should always basically choose the most expressive model class to optimize over, because it will always, never hurt you, right? You could always weakly improve by optimizing over a more expressive model class. This answer is actually also true in zero-sum games, right? So if the environment is adversarial or you're in a zero-sum game, the answer is also true. You should always optimize over a more expressive model class if you can, right? In general sum Markov games, that answer is not true anymore, right? So as I'll basically show you construction in which at Nash equilibrium, you're better off choosing a strictly less expressive model class to give you a higher payoff at equilibrium, right? So even with infinite data, infinite compute. And so this is our theorem. It says we look at this even in a very kind of simple normal form game that has strong monotonicity. So suppose that a game is strongly monotone, but your Nash equilibrium is not Pareto optimal, meaning that there's a point that you could move from your Nash, a coordinated deviation that would increase the utility of both of all the agents. So this is definitely not true in zero-sum games. In zero-sum games, all Nash are Pareto optimal, right? Then there actually always exists a unilateral restriction of your own action set, such that the Nash equilibrium in the new action set will yield a better payoff, right? And so choosing a model, and so the proof is, the idea that you should kind of keep in mind is that choosing a model class to optimize over is a form of commitment, and which gives you a first mover advantage, and it's not always best to commit to the largest model class. And in some sense, the takeaway is that infinite data and infinite compute, less expressive model classes can actually give you better equilibrium outcomes. So this should be kind of very counterintuitive. But in game theory, this shouldn't be too surprising. It's kind of full of examples like this where, you kind of restrict your strategy space and all of a sudden things get better, right? The most famous example is maybe Bray's paradox in routing games, if any of you are familiar with those. Right? I take away a road in a network, and all of a sudden the social welfare, everyone's utility gets better at equilibrium, right? And this is kind of something similar to what's happening. Great. So here's a construction of exactly what I showed you. We'll come up with a construction in a two-player general sum Markov game. So it's going to be an infinite horizon Markov game. And we're going to have two players. We're going to have n states and then two actions for each player, either 0 or 1. And this is our MDP. It's a very simple structure. Player 2 is actually going to control the state transitions. And player 1 has increasing payoff in larger states. So player 1 wants to push the system as far to the right in this MDP as possible. But player 2 is the one who controls the state transitions. Great. And so these are our kind of nested sequence of policy classes for each state. We'll just define a nested class of policies, right? The most expressive policy that you could choose is just from the simplex. And then we'll just constrain the simplex over and over again until we get the policy that's just a uniform policy. Okay? And we're also going to make it so that player 1 always has a dominant strategy in every state to always play A is equal to 0. And then we could actually compute their Nash strategy in each state for a given policy class is going to be given by this, which is basically their upper bound given this policy class. Great. And what we can show is just in this very simple construction, as our policy classes get more and more expressive, our utility at Nash kind of uniformly decreases. Or basically monotonically decreases. And so we've come up with a very kind of simple construction where the least expressive policy class actually gives you the highest reward at equilibrium, right? And so this is just a very simple construction that more expressive policy classes don't necessarily yield, the highest reward in games. And so basically choosing good function approximators in general sum games is highly non-trivial, and it could actually hurt your equilibrium performance to choose, extremely expressive policy classes, even with full information and perfect computation. But nevertheless, using function approximation in zero-sum Markov games is actually quite similar to reinforced learning, and so that's what we'll use in the next part of the talk. But I'll leave it there. So happy to take questions. Otherwise, we'll leave it there. Thanks. Yeah, go ahead. I can show you this. So, sorry, let me pull this back up.
There's the
So here there's no min-max structure, right? This is a general sum game.
right.
Yeah.
So if it's completely cooperative, then
If it's completely cooperative, then you're basically in just an optimization problem,
right.
right? In which case, you should always optimize over a more expressive set. You could always
Right.
put useful features zero. You could always set useful features to
So
zero.
adversarial and completely cooperative, you're fine.
Yeah,
General sum, there's an issue.
yeah.
So if we had to understand which model class does better for a particular structure of games, how would we go about that?
Yeah, that's a very good question. We thought a little bit about it, but it's actually non-trivial.
Right.
In some sense, the key is that you should essentially treat choosing a model class like solving a Stackelberg optimization problem,
Right.
where the lower level is actually the game that you play.
I see.
And yeah, solving that in general is quite hard because obviously you need to know something about your opponents to solve that inner Stackelberg problem. So in general, it seems like a hard problem.
So if you are there general sum dynamics where it is understood?
Not really, or not that I know of. Yeah. I think people just tend to, because things work out so well in, single agent RL and min-max optimization and zero sum games, they tend to just kind of blindly assume the same thing happens.
But this seems like a very general problem, right? It's not just about general sum games. This should be true in a different contexts as well. So do you think the same structure appears somewhere else?
I mean, you could, the structure really happens because we've moved away from our solution being the solution to an optimization.
Right.
Right? It's just an equilibrium.
Right.
And all this is really saying is that an equilibrium mapping is not monotonic,
Right.
right? In like the size of your space. Yeah, I don't have good answers. Yeah, these are all good questions. I don't have the answers,
Okay.
but it's, yeah, an interesting space.
So we can break for lunch, and the lunch is outside here. And anybody who does not have a badge can collect a badge from Kavyashree, and